Hello class, this is one experiment out of three. They're going to be remote. Unfortunately, you're not here. It's a very interesting experiment. You will like it if you do it. However, we can still help you out understanding this experiment. And this is acids, bases, the pH, and buffers. And I'll try to explain each one. An acid, by definition, if you take HCl and you add water to it, H2O, acid will dissociate, so H3O plus Cl minus. HCl is, by the way, it's a gas. Hydrochloric acid is not liquid, but it is liquid because we add water to it. And H3O, that's an abbreviation for us, which is H plus. So H3O and H plus are same, but H plus is like H2O plus H plus. That's what you got, the H3O. We call this hydronium ion. Let me write it down for you guys. It's called hydronium ion. The base, it's a substance that accepts proton from the acid. You have sodium hydroxide, for instance, NaOH, dissociate to Na plus OH minus. We're talking about the acid. You know the solution, it's going to be acidic or basic or neutral. The scale is called the pH scale, and it starts from 0 to 14. 0 being acid, 14 base, and in the middle you have pH 7, and that's neutral. So the neutral zone, where you have acid and base equal. If you have water, for instance, H2O is neutral. Therefore, the pH of water should be around 7. I'm talking about water, distilled water. There is no cation or anion added to that solution. We can assume that water can also dissociate. So if you have H2O plus H2O, dissociation will give you H3O plus OH minus. Now, water does not dissociate. That's very small amount of water that can dissociate. And you get this H3O plus, which is like H plus and OH minus. The Kw, the constant of the water constant, is equal, the dissociation constant that is equal 10 to the minus 7, because it's a neutral, times 1, this is for H plus, and 10 to the minus 7 for OH minus. It should be equal 10 to the minus 14. That's the Kw for water. So if I have the concentration of the base, I can calculate the concentration of the acid and vice versa. All right? So example, if I have the concentration of the base, let's assume OH minus concentration. I'm going to erase this, you guys, so I can show you the calculation here. So if OH minus concentration is equal 10 to the minus 5, what is the concentration of H plus? So we use Kw, therefore H3H plus is equal 10 to the minus 14 divided by 10 to the minus 5, which is equal 10 to the minus 9. You just take away, you change the 10 minus 5 to the numerator, plus 5 minus 14 give you minus 9. That's how you calculate the pH of substance. Now, the pH is equal minus log the concentration of the H plus. Okay, so there are two kinds of logs: log to the base 10 and log to the natural log 2.3 to the base 10. So we're using log to the base 10. We don't write 10. It's supposed to be log to the base 10, but no need to write that. So how we calculate the pH of solution? Very simple. If I have an H plus, the concentration of an acid, which is equal 10 to the minus 2. So what is the pH of this solution? Therefore, the pH is equal minus log the concentration of the acid, which is 10 to the minus 2. So because it's the base 10, log to the base 10, we just drop the minus 2 here. Minus 2 would be plus. So therefore, the pH of this solution would be equal 2. And therefore, if I have a solution of H plus 10 to the minus 2, that pH is plus 2. So therefore, it's acidic. Right? If I have a solution, H plus is equal 10 to the minus 10. What is the pH of this solution? Again, pH is equal minus log 10 to the minus 10. Minus 10 minus will be plus, so therefore the pH is equal 10. pH of 10 is basic, and so on and so forth. You get the idea now? You know how to calculate the pH to the base 10? It's very simple. We talk about the pH with acid and the base. Now we're going to talk about the buffer. What is a buffer and how you make a buffer? All right? And then we'll do the experiment after when I'm done. The buffer is made from a weak acid and its conjugate base. So if I take acetic acid, CH3COOH, this is acetic acid. Let me write it down, acetic acid. And then add to this the weak base. So what's a weak base? Take the acetic acid, CH3COOH, it dissociates slightly to CH3COO minus plus H plus. So the dissociation is so small, and therefore you get now this part here is the conjugate base. What's a base? Base accepts proton. This is negative, it can accept proton. So therefore, each weak acid has a conjugate acid, a conjugate base. Got it? Now if I mix the acid and the base, the weak acid and the conjugate base, I get a buffer. And we call this acetate buffer because it's acetic acid. So therefore, CH3COOH, the acid, and CH3COO Na, sodium acetate, and acetic acid, both will create for me a buffer. All right? So, again, the buffer is made from weak acids and its conjugate base, or weak base and its conjugate acid. So if I have ammonium hydroxide, which is a weak base, then it dissociates to ammonium plus OH minus, so that's the ammonium hydroxide. Therefore, if I take ammonium hydroxide and H4OH, that's the base, the weak base, plus ammonium, you can say ammonium chloride or ammonium bromide or something. So therefore, the base, the weak base, its conjugate acid, this will form a buffer. The question is, what is a buffer? A buffer is a substance that resists the change, right, in pH. In our body, we have the bicarbonate as a buffer. The bicarbonate buffer work as a scavenger for acids and bases. So therefore, if you have a blood pH 7.1, it stays 7.1. Why? Because of the buffer that we have, the carbonate buffer, the bicarbonate that is. This is the bicarbonate buffer. That's made from carbonic acid, which is weak acid, and sodium bicarbonate or potassium bicarbonate, right? So therefore, the bicarbonate buffer, right, will resist the change of pHs, all right? And we're gonna see that in our experiment also. So we're done with this theory, the base, the acid, the buffer, and so on and so forth. Now we have to go through the experimental part, all right? We need to measure, in this experiment, we're gonna measure pHs. all our experiment depends on the measurement of pH. So how we measure the pH? There are three ways to measure. We can use an indicator, and the indicator has different color in different pHs that can be used, or we can use a pH paper that will give you the color of the pH when you dip it into their solutions, or we can use what we call the pH meter. The pH meter, you just measure the pH directly. So we're going to try to use these. Number one, we're going to use the pH indicator. What's the pH indicator? Our indicator is the Cabbage. We have Cabbage, we made Cabbage, and I thank Kristen who made this solution for us. Thank Kristen so much for what she did for us, that she prepared all these experiments, and I appreciate her, and I'm sure you do appreciate her too. Kristen is in charge of the lab at Coastline Community College. Now, I had on the board the reference color for pH using the Cabbage color. You can do it at home, by the way. You can take red cabbage, boil it, and use that water. The red cabbage is like that. When you boil it and you filter, you get this solution. That's a red cabbage. This can be used as indicator. And I did it for pH from 1 to 12. I'm going to show you the color I get using this pH, using the cabbage as an indicator. pH 2, that's the color. So you write it down and say if you have a solution that an acid, right, and has that color, then you say your acid has a pH of 2, according to my indicator. Is that clear? Then I did that, add the cabbage to pH 3, if I can find it. And that's the color that gave me the cabbage with pH 3. Got it? Then we have pH 4. That's the color that I get from pH 4. Okay. And then we have pH 5. We started getting, it was pink, now it's changing the color a little bit. That's pH 5. Then we have pH 6, a little bit darker. And then we have pH 7, almost now blue, going to purple, start to purple, of course. I hope you can see the color, you guys, so you can tell. I hope it's clear for you. And then we have pH 8. Oh, this is really blue, I think. Okay. Then we have pH 9. And then we have pH 10. So now, and pH 11. And pH 12. Okay, so anytime I have to use the cabbage, this color will let me know what pH we have. If the solution of the acid I have, or the solution I have, give me this color pH, this color is pH 7. So I say, well, my solution has a pH of 7. It's a neutral, and so on and so forth. That's what we use the cabbage for, right? It's a reference color for pH using cabbage solution. Got it? Now, I can use the cabbage again to use this household cleaner. I have the vinegar here, and now we're going to add vinegar. We should add the opposite. Should add the cabbage back to the, the cabbage solution to vinegar. So I have the vinegar, and then I'm going to use the cabbage solution. That's the color I get. Compare this color to what we have. It seems to me it's acidic somehow. pH 2. Well, we know vinegar has acetic acid, so therefore it is acidic. We know that. We can use lemon. I have my cabbage solution. That's the color that I start with. And now I'm going to add lemon to it. And it's also acidic. So therefore lemon is acidic, and we know that. Lemon is acidic. Let me try something different. I'm going to add ammonia. What do you think about ammonia? What is ammonia? Acid or base? Ammonia is ammonium hydroxide, so therefore ammonia is a base. The base, according to my solution, they are in the blue area. So therefore, if my theory is correct, then the ammonia will change the color to blue. This is ammonia, this is the cabbage, and let's see how it works. Haha, bingo. Got it? All right. Okay, guys? All right, we have a color, blue. Let me check the color again. Oh, it seems like it's greenish color. I thought it was blue. I'm colorblind, I guess. All right. Now, let me show you this also. We did this with the cabbage. I'm going to switch to the other system. We're going to use pH paper. The pH paper has a color here. That gives you the color of acid to base. You see it there? All right. Now, if the ammonia is basic, I should get it in the region where it is green or blue or dark blue, whatever that is. All right, so let's do that. We dip the pH paper into the base, and that's the color you got. What color you guys you see? Blue. So therefore, if it is blue, then write down the pH paper give me a blue color. When you go at the blue color, it will give you almost the pH. It's a pH about between 12 and 13. That's the blue color. Okay. Now, I can use something else, which is the pH meter. The pH meter will also read the pH directly. So this is the base, ammonium hydroxide, and then we're going to use the pH meter. And it reads there 1109, probably will reach 12. That's the pH meter. Can you read it, you guys? It's digital. All right. So we did 3 different systems to measure the pH. One was the cabbage color, which we made. 2, the pH paper, that gives you a color from pH 1 to pH 14, and then the pH meter, which is digital, you just read it. Now we mentioned buffer. I'm going to use pH 4 as a buffer, and I'm going to measure the pH, or I don't have to measure it because it's pH 4. It says pH 4, and it is pH 4. So this is my buffer, and we're going to have 3 of those. 3 pH 4 buffer. Okay. On the first one, I'm going to add, I'm going to just add the cabbage solution, the first one. That's the color I have. On the second one, I'm going to use the same thing. I take a pH from this guy here. And it reads 3.71, 3.7. So therefore we are close to pH 4. So these solutions, the buffer 4, it has 3.7, or according to the cabbage, is also around 4. So we know now we have a pH 4 of this cabbage. All right? Now, we're going to prove that the buffer is a system that resists the change of pH. We're going to use water in one test tube. I have to find water somewhere. Oh. So this is water. I'm going to use 2 test tubes for this, for the water solution. 2 test tubes. Water solution. Okay. I'm gonna use cabbage again as a pH indicator for water. Color are almost the same because it's water, both of them. But we're gonna assume that water is a buffer. You got it? So water, assume water is buffer. Of course we know water is not buffer. And we're going to test this buffer. One time we're going to add a drop of acid, and one other time we're going to add a drop of base. Okay, ready? On the first test tube that has water, I'm going to add a few drops of the acid. 1, 2, 3. And we shake it. You see the color changed? Almost pink, correct? So therefore, the drops of the acid did change the pH. It dropped the pH from 7 to about maybe 2 or 3. That's water with acid. Let's do water with base. This is water and this is base. Water with cabbage and this is base. What happened to the color, you guys? Almost green, right? So therefore, it changes from 7 to about 10, 11. Got it? Now, we're going to have a buffer, like we did there. We're going to have 2 test tubes for buffer. One, we're going to add acid to it, and one, we're going to add base to it. All right? pH 4. Take some of these. Got it. Now, we're gonna add our indicator. And this is the color that I have with the indicator. That's buffer plus the indicator. Got it? And we're gonna add drops of sodium hydroxide to the buffer 4. We add the base. What color is this? It did not change, right? So the buffer resists the change in pH. The base did not change it. Acid will not change it either. Here's my acid, and we add a few drops. And the color stays the same. Is that clear, you guys? All right, so therefore, the buffer will resist the change in pH. Water is not a buffer. Hydrochloric acid itself is not a buffer, and so on and so forth. How the buffer is made? A weak acid and its conjugate base, or a weak base and its conjugate acid. All right? I think I'm done with most of this experiment. And enjoy the write-up. Let's see, that's about it.